Okay. Sorry for being late. Let's start today's seminar.
So how to just
Sorry.
how to go to the other slide?
Press this or why? Okay. This
And
button is fine.
once in presentation is already here. Right? Just cool.
Okay. So let's start today's seminar. Today's speaker is Dr. Nivedita Ghosh from
HRI.
HBNI.
HRI.
Sorry. HRI. Okay.
Yeah.
So we'll talk about Alleviating generalized two-Higgs-doublet model in the muon anomaly and lepton flavor-violating decay. HL-LHC.
Okay, thanks, Suro, for this introduction, and I will like to thank Professor Ko for inviting me. My today's talk is based on this particular paper. Okay. First I will motivate for this work, then I will discuss a little bit about the model, and then I will tell what is muon anomaly and what we have done in this particular work. Then I will discuss about the relevant constraints that are applicable for this model coming from low energy experiments. Theoretical constraints like vacuum stability, perturbative unitarity, constraints from B physics, electroweak constraints coming from STU parameters, and also constraints coming from collider searches. After that, I will talk about searching pseudo-scalar in this particular model in lepton flavor-violating decay modes, and finally, I will conclude. So we all know that anomalous magnetic moment of muon is a crucial observation which has still some room for new physics scenario. So the ongoing E989 experiment at Fermilab and the future E34 and JPAR experiments are expected to shed new light on this discrepancy between the standard model prediction and the observed data. On the other hand, though we are sure of neutrino oscillations and we know there is lepton flavor violation in the neutral sector, however, nothing has been observed in charged lepton sector. So from various low energy experiment, we have bounds on the branching ratios of these flavor changing neutral current decays and correspondingly on the associated couplings. So the experimental observation of muon anomaly and non-observation of this lepton flavor violation creates a tension in terms of the allowed parameter space for various models which individually satisfy these two results. So in this work, our goal is to satisfy both this muon anomaly and lepton flavor violating decays, and also to look for lepton flavor violation in collider experiments. So for that, we have chosen the simplistic extension of the standard model, that is 2HDM model. And the most general scalar potential can be written by this equation, where in general M12 square, lambda 5, lambda 6, and lambda 7 can be complex. But however, since we want a simplistic CP conserving scenario, we have kept them real. And these two scalars can be expanded in terms of this equation, and after electroweak symmetry breaking, the neutral component will get the vacuum expectation value, And the ratio of these two waves is a key parameter of this model, which is tan beta. Okay, so the singly charged Higgs and the charged Goldstone can be found as a linear combination of this phi1 plus and phi2 plus. And similarly, the CP odd scalar and the neutral part of the Goldstone can be found in a similar linear combination. For the CP even scalars, if we rotate the basis from a flavor to mass, this is the particular rotation by this angle alpha. And out of this two Higgs, anyone can behave like the standard model with mass 125 GeV. We will discuss about the particular choice, whether the small h or the capital H we are taking to be 125 GeV. Okay, so in general, to avoid tree-level efficiency, in two-Higgs-doublet model, people assume a Z2 symmetry, and for that, actually they keep this lambda 6 and lambda 7 to be 0. However, for that, there are like, depending upon the combinations, there are 4 types of two-Higgs-doublet models. Type 1, where all the up, down, and lepton couples to the doublet phi2. In type 2, where phi2 couples only with the uptype 4, and the down and lepton couples to phi1. In lepton specific or type X, phi2 couples to both type of quarks, and phi1 couples only to leptons. And in flipped or type Y, the uptype quark and the lepton couples to phi2, and the down type quark couples to phi1. However, in our scenario, we have not assumed any particular Z2 symmetry, and as a result, there will be tree-level efficiency. So unlike the other 4 cases, in this particular case, you can see all the uptype, downtype, and lepton, those can couple to both phi1 and phi2. Now, if we expand this Yukawa in terms of waves and physical fields, we can get the Fermion mass matrix as the following. Now, you can see in the left-hand side, there is only one unknown, and in the right-hand side, there are 2 unknowns. So, solving this equation is impossible if we don't assume any particular assumption. And for that, we have taken that Y2U, Y2D, and Y1L, those will remain non-diagonal, giving to the tree-level efficiency in the Yukawa sector, and the other remains diagonal. So, if we write these in terms of the physical basis, so couplings with the neutral sector is like the following, and here the M's are the basically diagonal mass matrices of the fermions, and these U's are the unitary matrices required to diagonalize that MF. Now we want these matrices to write in terms of some dimensionless parameter chi's, and afterwards we will call these chi's to be the lepton flavor-violating couplings like YE mu, Y mu tau, or YE tau. And in general, chi ij need not be equal to chi ji. However, for simplicity, we have assumed them to be equal. Similar to the neutral sector, the charged Higgs boson Yukawa couplings can be written as following. Where the zeta couplings are given by one diagonal term and other non-diagonal. So, discussing the model part, let us now discuss the muon anomaly part. So, in standard, like in classical quantum theory, we know that the gyromagnetic ratio for the muon is 2. However, it will receive a correction from UED, hadronic and electroweak corrections. So the value shifts from 2. And in standard model, the value reads this one. However, the recent muon G-2 collaboration has published their result. And along with it, if we combine it to the older DNL data, the mu gives this value. And the difference between equation 15 and 17 gives rise a 4.2 sigma discrepancy with the standard model, which urges us to look beyond the SM. So in this work, we have taken into account the one loop contribution as well as the two loop contributions. Now, apparently it may seem that in two loop it will get a suppression, and that is true. But above that, we can also get an enhancement of m square by mu square, where m is the heavy mass running in the loop. So, in some parameter space, for this particular model, the two loop contribution dominates over one loop. So there will this is the neutral scalar diagrams. There will be these charged scalar diagrams, and also these legs replaced by the same type of charged scalar and the charged boson. In particular, for this work, we are interested in for collider perspective, low mass pseudoscalar. And for that, we have seen that this particular diagram is very much important. And if you go earlier, you can see from this term, like this, there is a tan beta coupling associated with this particular diagram. And we see as tan beta increases, there is more favor for this muon G-2. Now, for this scanning, we have chosen the Yukawa couplings fixed at this. The particular choice we will be discussing in a bit. So, from this muon anomaly data, we can conclude that low Ma mass and large tan beta are highly preferred for this muon anomaly. So, the same sort of diagram will appear to the low energy experiment.
Excuse me.
Yes.
Excuse me. In the previous slide,
Yes.
are there any lower bound on the MA?
Lower bound on MA, you mean? Okay, so here.
For example, if A is light enough, then Higgs can decay into a pair of pseudoscalars, right?
Yes, yes. That bound.
And pseudoscalar to BB bar, etc.
Yes, yes, that we have taken into account. I will just discuss it from the collider when I will discuss the constants coming from collider.
Okay. Yeah, thanks.
Okay, so the same sort of diagrams will also contribute to mu2 E gamma, tau2 E gamma, and tau2 mu gamma. And there will be also constants from mu conversion and mu2 3E decay. However, the strongest bound comes from this make collaboration branching mu2 E gamma. And on a passing comment, I will just try to make this like in this mu conversion. In future, they are planning to do it with aluminium, and the expected bounds are like 10 to the power minus 15. So in future, probably mu E conversion will be the stringent bound that we need to consider from low energy experiments. Here also similar to the muon anomaly, we have taken both one loop and two loop. However, we have seen that in the region of parameter space, for tau2 E gamma and tau2 mu gamma, two loop contributions are merely 2% of their one loop counterpart. However, for mu2 E gamma, the two loop contribution induced 3 times enhancement to the one loop amplitude. So to be safe, we have considered both one loop and two loop for this three process. And here I just want to discuss why that particular choice of the Yukawa couplings were so fine-tuned. Because we see that y mu e that has to be less than 10 to the power minus 6 to have sufficient overlap between muon anomaly and mu2 E gamma. However, if we take the coupling y tau e to be 10 to the power minus 4, there is no overlap between these two data. Similarly, if y mu tau is 10 to the power minus 4, there is no overlap with muon anomaly data. So to satisfy all these three couplings, we need this fine-tuned couplings to satisfy, to get an overlap between the muon anomaly and this low energy experiment data. So after that, we have considered the vacuum stability requirements. And if we write the mass in terms of these lambdas, we can see the mass difference of charged Higgs and pseudoscalar Higgs is proportional to this lambda 5 minus lambda 4, which is nothing but constant from this particular equation. And also above that, if we demand perturbative unitarity, like all the lambdas has to be less than 4 pi, and we scan the parameter space in this particular region, we see for low Ma mass, there is a bound on the charged Higgs mass, which has to be less than 170 to 180 GeV. And in the Ma tan beta plane, we see that although high tan betas are allowed, but low to moderate tan beta are more favored. Now coming to Professor Koh's question, like we are saying here the pseudoscalar is very light enough. So definitely we need to consider this PP2 Higgs to AA process and in this mu tau tau final state or maybe BB final state. So for that, to satisfy the bound from experiment, we need this coupling to be very small. And you can see that to keep this coupling very small, and from perturbative unitarity, we need that M12 square has to be mh square by tan beta. And this scenario is only satisfied when tan beta is less than 10. And the mass gap between mh and minus small h, I mean the mass gap between these two CP even scalars are not very large. So this region is phenomenologically viable. However, if you remember this muon anomaly plot, that tan beta less than 10 is possible when MA is also less than 10. So it's very constrained parameter space. So the other case which we can consider is when our M capital H is 125 GeV. Like the higher CP even Higgs is 125 GeV. However, there will be another bound from left, which implies either the pseudoscalar or the MH can be less than MH by 2. So here, since we have considered this MA to be like 20 to 30 GeVs ballpark of that, so MH we have taken in this particular case to be 120 GeV. And in this particular case, we see that with proper choice of M12 square, we can have the pseudoscalar mass greater than 10 GeV with moderate tan beta. I guess I answered your concern. Hello? Professor Ko, am I audible?
Not sure.
Okay, so should I proceed?
Yeah.
Yeah. Can you just speak louder? Mass of?
To be smaller. Which bound is which observable is giving the bound, right? Which observable is giving the bound of the
Oh, okay. So if you're like Higgs, like the mass of pseudoscalar is less than 125 by 2, that is like 60 GeV, then there will be this particular mode PP to Higgs to AA production. Like if 125 GeV is greater than, I mean, it can go kinematically to a pair of AA. So there is a search for this by CMS collaboration, and they have put upper limit on this A going to mu mu and A going to tau tau, this particular final state. So since they don't have seen any excess, so we need to satisfy this particular data. So it is coming from the CMS collaboration data in this particular. Why are you asking this? Sorry? Yes, to satisfy this coupling has to be very small, else it will be above the bound and the parameter will be ruled out. Since we don't want this, we have to keep this coupling to be very small, and from there we just need this thing. Yes, yes, I will come. So, okay, so in this particular case, our in capital H, the higher CPFN Higgs is kept at 125 GeV, and the other one is kept at 120 GeV. Now, sorry, there will be bounds coming from B physics, and the strongest bound comes from B2S gamma, which allows the charged Higgs mass to be greater than equal to 150 GeV for this particular lambda TT and lambda BB coupling. So there will be the constraint coming from the oblique parameters, and we can translate it in terms of MA and MH and minus MH plus this mass difference plane. And you can see that 30 to 40 GeV mass difference is allowed in this fan. So since we have chosen MH plus to be 150 GeV, we are forced to choose MH to be 120 GeV. Now, there are various constants from collider, like Leif has constant on the lower limit of H plus mass, which is 80 GeV. And also, since the charged Higgs mass is 150 GeV, which is less than the top mass, the charged Higgs can be produced from the decay of this top quark in this particular mode. So we have also checked these limits, and those are satisfied. There will be another limit coming from the neutral scalar going to ZA decay mode. However, these particular constants are applicable when the heavier CPFN Higgs is greater than equal to 200 GeV. However, in our case, since it's 125 GeV, this particular surge do not have any considerable effect on our parameter space. Now the severe constant will come from this 125 GeV going to tau tau, mu tau, and also the efficiency decay modes like mu e, e tau, and mu tau decay mode. So since we are strictly conserving ourselves to the alignment limit where cos beta minus alpha is approximately 1, and you can see from previous slide that the 125 GeV in our case, that coupling is that coupling is proportional to sine square beta minus alpha. So we are trivially satisfying this constant, and we do not need to worry about anything else from collider. Okay. So now, since we are talking so much about this light pseudoscalar, so we want to consider the particular decay mode in lepton flavor violating decay. That is, the pseudoscalar goes to L and the tau, where tau decays lepton. So the particular channel of interest is like E plus mu minus miscignity or E minus mu plus miscignity. So we need to consider these particular background processes like tau tau, E mu mu, TT bar leptonic, semi-leptonic, W plus Z's dye boson and standard model Higgs production. Okay, so here we have given these three benchmark points, and the other MH plus, those are fixed, and the production cross section at 14 TeV LHC. Now you can see that we have varied the mass from 21 to 27 GeV. That is in a very narrow region. But the reason is that due to satisfying all these low energy experiment constants like mu 2 gamma and all those, we have to keep those couplings to be very small. And it turns out to be that the branching ratios in these particular modes are like 10 to the power minus 7. So we cannot go beyond this mass to see something or predict something in the collider. Now we have first done the card-based analysis, and for that we have written the model file in fine rules, and we have generated the events in MATGraph and showered by PK, and detector simulation is done in Delphis. And to generate our signal and background events, we have employed the following pre-selection cards. And also, since our signal don't have any jets, so we have also put these PZ vetos to eliminate the backgrounds coming from TT bar and those. So in this diagram, we have shown, since we say that we have two leptons, so we have plotted the transverse momentum for the leading lepton and the sub-leading lepton. And in our case, the two most dominant backgrounds are TT bar and tau tau. So since we demand our signal has two isolated leptons, and there is no any third lepton, so we reject any third lepton with PT greater than 10 GeV. Also, since our signal is hadronically quiet, we put a Z veto of 20 GeV, and this particular curve helps us to reduce the TT bar semi-leptonic and W plus Z's background. Now comes the transverse missing energy variable. So for the signal, the transverse the missing energy can come only from the neutrinos, and for tau tau also, the neutrinos are produced back to back, so they tend to appear at very lower beam. However, for TT bar, the neutrinos come from the three body decay of the top, so they tend to populate the whole space. So it's by putting a cut like 30 GeV or something, we can get reduce of this TT bar background. Now the invariant mass of the lepton pair, it's very good observable in the sense that the invariant mass of E or mu mu that will peak at Z boson mass, and for a suitable by giving a suitable cut, we can get rid of this tau tau background and signal. The other variable is the collinear mass, which is nothing but the reconstructed mass of the pseudoscalar. You can see like for BP1, BP2, and BP3, the peaks are at 21 GeV, 25 GeV, and 27 GeV. So this cut also helps to reduce this tau tau background. Then comes the transverse mass variable, which is the combination of the lepton PT missing energy and the angle between the lepton and missing energy. This cut helps us to reduce the TT bar background. And also the azimuthal angle between these two leptons. For tau tau, they will be produced back to back, and so they peak at pi. Wherever there is no such particular relation for this TT bar and this background. So this cut helps to get rid of tau tau. So with this particular choice of cut, here we calculate the significance. And as I was mentioning previously, like if we even change the mass from 21 GeV to 27 GeV, we can see the significance at 3000 femtobarn inverse drops from 5.7 sigma to 0.6 sigma. This is the demerit of this cut-based analysis, because for this 27 GeV mass, it cannot discriminate between the signal and background. So after that, we tried to improve our analysis by artificial neural network. We have taken these variables only that I discussed, and for ANN, we have chosen a network with 4 hidden layers with activation curve ReLU, and the batch size is taken to be 100 and the number of epochs are 100 in our case. And we have used 80% data for training and 20% for validation. And we have also checked explicitly that our network is not overtrained. Since we had beforehand idea like MLL, the invariant mass of the dilepton pair and the n collinear masses populate which region. So for training, we have actually applied these two cuts beforehand to train the network in a much better way. And we have seen that the accuracy we get is 99% for BP1, 98% for BP2, and 96% for BP3, which indicates like good discriminating power between signal and background. And also, like the area under the curve is also close to 1, so it's well trained. So with this particular setup, we get this ROC curve, and we can calculate the significance with cuts plus ANN, and we can see like previously for BP3 the significance was 0.6 sigma. Now it's like 3.2 sigma. So all our benchmarks we can probe with significance greater than 3 sigma. So like 99.7% confidence level. So that brings me to conclusion. So we see that the long-standing problem of muon anomaly and LFV constants can be solved simultaneously in this generalized two-Higgs-doublet model with particular flavor-changing coupling, and the CP even and charged Higgs mass fixed at 120 and 150 GeV respectively. We also look for flavor-violating decay modes in L plus L minus vicinity final state. And we see that with a rectangular cut-based analysis, this at 3000 femtobarn inverse luminosity, the significance drops from 6 sigma to 1 sigma as the mass of the scalar increases from 21 to 27 GeV. However, we can improve definitely this in using artificial neural network. So that's all. Thank you.
Thank you for the nice talk. Any question? So how do you understand this large improvement in the AM? So your hep-ph analysis gains confidence, but if AM includes this significant, then there must be something missing in the calculation.
Sorry, I can't get your question properly. So what?
So I'm just trying to understand what was missed.
Okay. So
Because ANN improves your shipment.
yes, if you see this thing, yeah, you can see like for BP1 in card-based analysis, when we are just putting some rectangular cards by seeing the observables. So you can see for BP1, the effective cross section is 0.026 or something like that. However, for BP3, it's order of magnitude less. So that's because we are putting the cut in some wrong way, and or to be more specific, we can say that we are giving cut in some way where the benchmark is almost mimicking the backgrounds, and it's very much impossible to choose a particular cut to distinguish the region over here. So that's what the neural network does.
So can you come back one slide?
So hello.
Yeah.
I have one question. So according to your conclusion,
Yes.
150 GB charge disk is still allowed by various constraints?
150 GB. Yeah.
Charge disk.
Yes, it's allowed. We have checked these. I think you were considering for this PP to TBH mode. So we have checked this thing, and yes, for this particular mode, it's allowed. Yes.
How about in B physics?
Yes, from B physics, it has to be
like a bit of S to mu mu.
Yes, I can just give you the details. So from BS to mu mu, these
Yes.
constants like tan beta less than 2 is for low mass region. However, for like higher charge Higgs mass, this bound is much more relaxed. So 150 G is not ruled out.
Okay, thanks.
Yeah, sorry, was saying.
Other question?
Yeah. Can you go to slide number 90?
I don't know, it should work from here. Yes.
What is the reason behind this controversy? Just this meaningful the tool is important, right? But not for tau to gamma and tau to
Yes. Like you can see this tau to E gamma and tau to mu gamma. These factors come with couplings like Y tau E and Y tau mu, and with the factor m tau. However, for this mu to E gamma, there is this always how do I say? Like there will be some terms like Y mu E at one side, and there will be the couplings associated with ME, and the other side it will be M mu times Y mu tau. Like, so there will be like, I don't know how to explain this. Like it's between the competition of the Yukawa times mass for this tau to E gamma, and like this tau to E gamma, this coupling is solely dependent on Y tau E coupling. However, for this mu to E gamma, there is always competition between the couplings times the mass. So if you go to the higher loop, there will be enhancement with this tan beta. Like I cannot say it very in a naive way, but if we do the calculation, we have seen like this happens. And this is because of this coupling in one case, which is dependent solely upon the coupling, and for mu to E gamma, it's always the competition between the tau mass and the Yukawa coupling.
And even higher load competition can be there.
That one has to check, like I guess for this 2-HDM, not the higher one, because people generally talk about up to 2 loop. Because if it happens, like if we go to higher and higher loop, it increases, then there is the theory has to be like questioned.
Other question?
How does HL compression get derived from some other?
How does?
So, HL some other interacting with very
HFF.
maybe up to 50 degrees.
Page 8, okay.
So it is a standard beta becomes that so for the it is coupling becomes that there is some model.
Yes.
It is satisfy the same.
I'm not very sure about your question. This is
So like some of the really things and standard beta equal one and sign beta minus alpha equal one.
that is taken care, right? Because I told like this standard model Higgs, that is in the limit cos beta minus alpha approximately 1. So in the alignment limit, these all the standard model Higgs decaying to the other things are always taken care of.
So but neon given require.
In standard model, there is no pseudoscalar, right? I'm not getting the question probably.
So the standard beta require to get very large.
Yes, because of this these couplings.
So then in the only to consider with it's then interrelated.
Sorry.
And
What is the question?
so the coupling somewhere in the film.
That is not changing because here I'm not telling about the small h, it's the capital H, the other Higgs.
Any other question? So it seems it's time to end. Let's thank first again. Thank you very much.